All right, well, coming to you from cyberspace, we're going to talk about, we're going to work a problem today in statistics. This is part 3, the 3-part series, supposedly meant to simplify statistics for you. So that in 30 minutes, you kind of got the whole thing, okay? So buckle up. We'll set the capsule down and we'll get busy. You know, I can understand. I went through a period in graduate school where I was just furious. I was so frustrated and upset because I was taking a very elementary, quote, descriptive statistics course and was totally lost. So I had wished, in retrospect, I finally got it. It was a 16-week term, and I think I got it around the 14th week. Up until then, I was just shooting in the dark, getting all kinds of help. Everybody seemed so smart at it, and I felt so stupid. You know, it was really difficult for me. And I think it was made more difficult because people didn't get, you know, they like all knew it, and they were like impatient, like, you know, just catch on, let's go, this is not exciting, let's get to the exciting stuff, like solving big problems. But they forgot some very fundamental things like what the symbols meant and what we were just, what are we trying to do? You know, why are we doing this? So a little refresher, we're trying to represent a group of people usually, or it could be alligators, a population of something, or a sample of a population. We're trying to get a quick take, a grasp of where they are in relationship to, you know, hat sizes, preferences on toothpaste, standardized test scores, etc. What I'm going to do is we're going to do a little problem together here, work through this. So let's see, I want to do this way. So we're going to start with a set of test scores, okay? So X represents, I think if I look through the paper, I can see better. So X represents the column where the scores are. So you can see here, just look at this column. There's, the scores are a 9, a 9, a 9, a 5, a 4, and a 3. Did I say 6? A 9, a 9, a 6, a 5, a 4, a 3. So there's 6 scores. Small class, or is it a sample? Well, this is a whole population. We can tell right away because we're using a big X. If it was a sample, this would be a small x right here. That would be a dead giveaway. The other thing would be this mu for average would be a big M instead, as well as here be a big M. So we can just tell by looking at the top of this, if this is the way it was given to us, that we're dealing with a population. If we were reading the problem and constructing this chart, which is what I do, I like to construct the chart all the way through so I get a grasp, make sure I've done things correctly, I got a grasp of what's going on. If I was constructing it, I would want to know if it's a population or a sample. If it's a population, we've already gone over this. You know, you use one set of symbols and a way of configuring your sum of squares. And if it's a sample, some other symbols and a different way of doing your sum of squares, n-1, just as a little refresher. Okay, so here's the first thing we do. We've got our set of scores, 6 scores, and just stay with me here. That averages out to be 6, a score of 6, because there's 36. When we add them all up, we divide by 6, and lo and behold, we get an average. My pointer, we get an average of 6. There's our average. Okay. Now, the next thing we need to do is subtract the average, the mean, from each of these scores. Okay. So we've gotten the average from this column of 6. Now we're going to subtract it from this. And so here we're going to, and then we're going to put the difference here. So it's going to be the score minus the mean, or the average. So we're going to get, does this show it better? Yeah, nah, sorry. I'm going to get better at this. Okay, so we subtract 6 from 9, we get 3. 6 from 9, we get 3. 6 from 6, we get 0. 6 from 5, we get -1. 6 from 4, -2. 6 from 3, a -3. Okay, now, they don't do this in the book, but I just want to show you something. If you add these all up, you get 0. You'll always get 0. You have to, because what you've done is you've subtracted the same number from everything, and when you add it up, you're going to get 0, because these are away from the average, these are towards the average, or these are plus average, these are minus average, and they even out, and so you're going to get 0. So we don't even mess with that. So it wouldn't every time. So we couldn't really work with this. The formula, you know, the ability to use a formula would die right here, because we'd always be using 0, and 0 times anything is 0. So boom, end of story. So we don't work with that. We need to create a set of figures that will keep things the same in the way they're related to each other, but without everything totaling up to 0. So what we do is we square these. We take them times themselves, and that gets rid of these minus signs. Okay, so 3 times 3 is 9, 3 times 9, 3 is 9, 0 is 0, 0, 1 to 1 is 1, because 1 minus 1 times itself is a plus 1. Don't ask, just go with it. Minus 2 times itself is plus 4. Minus 3 times itself is plus 9. Those are your squares, okay? Those are your squares. So, and this is the mean. So this is the sum of squares. And then you're going to add them all up, and you get 32. And that's your sum of squares, 32. Okay. Now, we want to know the variance. Okay. And this is real easy to do, because we just take 32, get the average of your sum of squares. So you got 6 scores still. You divide this number by 6. Okay. You get 5.3. So your variance, or your squared, I wish I remember the name of the symbol, sorry. Your variance is 5.3. And your standard deviation is going to be the square root of your variance. So there it is right there, 2.3. 2.3 times itself equals 5.3. Okay. So now you've gotten your sum of squares, your variance, sum of squares, your variance, and your standard deviation. Sum of squares divided by 6 gives you 5.3. That's your variance. Square root of variance, 2.3. Okay. If it was a sample, instead of a population, besides the symbols up here being a little different, you would take n minus 1. So you would subtract the 6. Instead of dividing 32 by 6, you would divide the 32 by 6 minus 1, or 5, and you would wind up with 6.4 as a variance, and the square root of that would be 2.53. So the difference in a sample from a population would be 2.53 versus 2.3. Okay, maybe not a big deal, but it tells you something. Okay, it tells you how close your sample was to your population. Okay, if you were comparing 2 different groups. But that's neither here nor there. The important thing was to see how to work the problem. I hope that made sense to you. It's really, the best way to do this is just do a chart until it all falls into place for you. And simply all we're looking for is how far people deviate from the mean, and how spread out they are from one another. You know, and just trying to be as accurate, get an accurate thumbnail as we can of a set of scores about something. Hope that makes sense. If not, email me at asdjones@gmail.com. I can also send you a set of these crib sheets. Be glad to, free of charge, at A as in Apple, S in Sam, D as in Dog, Jones, at Gmail. G as in gerrymander. .com. It's been a pleasure, and hope this helps. Like to have your feedback. Just let me know if this was terrible, I should erase it, or if it was helpful. I don't need any kudos. Just like to know if it's helpful. As a teacher, you like to people go, "Oh, I got it," or "Man, you confused me even worse." So hopefully that helped. If it did help, then in 30 minutes, you kind of got a grasp of the whole thing about statistics, simple statistics. Have a good day. Better still, make a good day. Dr. Zest signing off here. That's all, folks.